What's up, everyone? In this video we are going to tackle Fun with Derivatives Part 2. So remember, we talked about finding derivatives should now be easy. It's what you could do with derivatives that's super fun. And we've been tackling 4 things. The first 2 we did in the previous video, Part 1. Well, now we're in Part 2. So we're going to focus on the third and fourth things we could do once we found a derivative. So the third thing is find the equation of a line tangent to a function that is parallel to a given line. What? You may say, we'll talk about it. Give me a moment. It's actually pretty easy. And the fourth thing we're going to do is find the equation of a line tangent to a function that runs through a given point that's not on the function. Number 4 is by far the hardest problem that we're going to take a look at. But listen, here is the dealio. I have to make sure you guys understand this. If you're good at finding derivatives, that's not the difficult part of this. The difficult part of all of these types of problems is algebra. If you're bad at algebra, you might have the best understanding of derivatives. You might have the best capability of finding derivatives. But if you're bad at algebra, well, to be honest, you're going to really struggle with these. And to be honest, if you're really bad at algebra, well, then you're probably really bad at finding derivatives too, because so much of finding derivatives is really all about algebra, as long as you know the rules. But let's dive right into the third type of problem first. All right. So a picture is truly worth 1,000 words here. So what we're doing with this third type of problem is we're finding the equation of a line tangent to a function that is parallel to a given line. So here's what I'm going to give you. I'm going to give you the 2 things that we see in this graph. I'm going to give you a function, f of x, and I'm also going to give you another line. We'll just call this a line, right? And I want you to find a tangent line to the function that is also parallel to this blue line. So we're looking for a line that is parallel to the blue line and tangent to the red function. So very, very specific line, and only one such line exists. Again, parallel to the blue line, tangent to the function. So if I'm just trying to draw this roughly, we're talking about that line right there. Sorry for my poor drawing abilities, but I tried to make that green line look parallel to the blue line, but also tangent to the given function. So again, this is going to be our goal, but you need to understand what you're trying to do. All right, let's dive right into our first example of this type of problem. So we want to find the equation of the line that is tangent to the function negative 4x squared plus 6x minus 6 and parallel to the line 6x plus y equals 8. I actually already have a graph set up of this. So the blue is the function that we saw a moment ago, and the red is the line that we want to be parallel to. So once again, my thought process is I'm trying to find a line that is parallel to that red line. And there's millions of lines that are parallel to that red line. And the key thing you have to remember is that the same slope. All parallel lines have the same slope. So as long as I have the same slope as that red line, I will be parallel to it. And there's going to be millions of answers for that. But there's only going to be one line that is also tangent to that blue function while at the same time as being parallel to the red line. And of course, that's my goal. All right, so the first thing you have to understand is if I'm parallel, it means I have the same slope. So I actually already know my slope. So all I got to do is find the slope of this line, and the best way to do that is to put it into slope-intercept form, where the y is by itself. So all I got to do to get the y by itself is subtract the 6x over. And if you have learned anything in algebra, you immediately know that the slope is negative 6. So I already know my slope. So if I go back, the red line has a slope of negative 6. Makes sense. But there's millions of lines that have a slope of negative 6. I want the line that is also tangent to my function. The problem is I don't know the point of tangency, right? If I'm just kind of eyeballing it, it looks to be somewhere in this general vicinity around here, because I'm kind of just eyeballing my line that's going to be coming in and being parallel. Again, really rough because I'm terrible at drawing lines, but you get the idea. I'm trying to get this rough line that is going to be just tangent to that function and also parallel to that red line. So I need to find the point of tangency. I need to find the point x comma y on the function that is tangent. So how the heck can I do that? Well, the derivative. Remember what the derivative does. The derivative, you plug in x and you get the slope. But here's the key thing. I already know the slope. So what I could do is take the derivative, set it equal to my slope, and solve for the x value. But of course, the first thing I need is the derivative. And I'm not going to walk through how to find the derivative. I'm going to expect that you guys know how to find that derivative once I show it. And voila, there's my derivative, negative 8x minus negative 8x plus 6. Hopefully that's a pretty easy derivative to find using the power rule, the constant multiplier rule, and the constant rule. Really easy rules there. All right, so now I have my derivative. But what you need to truly understand is that what does negative 8x plus 6 represent? Negative 8x plus 6 represents a formula to find the slope at any given point. So it finds slope. So the answer to a derivative, the result of a derivative, is the slope. But once again, I already know the slope. So what I could do is work this in reverse. You know, if you think about what we did in part 1, fun with derivatives part 1, is in all those problems, we needed to find the slope. So we plugged the given x into the derivative and we found the slope. But what we want to do now is work backwards, right? I know the slope is negative 6. I want to find the actual x value that would produce that slope on my function. That's the point of tangency. So, how simple is this? All I got to do now is solve. So let's see, I'm going to subtract 6 over, so I get negative 8x equals negative 12. Divide everything by negative 8, and I get x equals, let's see here, 2 negatives make a positive. 12 and 8 are both divisible by 4. So let's see here, I get 3 halves. 12 divided by 4 is 3. 8 divided by 4 is 2. So there is my point of tangency. So the actual point I'm looking for is at an x value of 3 halves. 3 halves is 1.5. So that's going to be right here. And of course, I didn't do a great job of drawing that. But again, it was just a rough drawing. Now, the other thing I need is the y-coordinate. Remember, I want to find the equation of a line. The equation of a line requires a slope. Hey, I already have that slope. Check, check. It also requires a point. And I now found that the point of tangency has an x value of 3 halves, but I need the y-coordinate as well. How do you find y-coordinates? That's what functions do. Good old, good old school functions, not derivatives, just traditional functions find y. So now I'm going to go ahead and plug 3 halves into that to find my y. So my y value is going to be negative 4 times 3 halves squared plus 6 times 3 halves minus 6. And this is going to require, again, most kids are going to grab their calculator, but I'm going to attempt to do this on my own. Negative 4 times 9 fourths plus 6 times 3 halves is 18 halves. Minus 6, and all of this is going to be very reducible. Let's see, that results in negative 9 plus 9 minus 6, which negative 9 plus 9 is 0, minus 6 is negative 6. So there's my y-coordinate of negative 6. So again, go back to that graph. Right here is my point of tangency, and it happens at an x value of 1.5 or 3 halves, and it happens at a y value of negative 6. There's my point of tangency. So I was a little bit off when I drew my picture. I'll try to make it a little bit better this time. And there it is. So there is my line that is parallel to the red line and tangent to the given function. So now I just got to figure out what that line's equation is. So that's going to be y plus 6 equals my slope of 3 halves times x minus 3 halves. Whoa, 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 whoa. I am so sorry. I'm so sorry. I made a mistake there. My slope is negative 6. My slope is negative 6 right there. All right, my x-coordinate was 3 halves. So once again, y minus the y-coordinate creates y plus 6. My slope is negative 6. Times x minus 3 halves. And the cool thing is you could check all of this in Desmos if you know what you're doing. So let me show you. So in Desmos, I went ahead here and graphed the original function, negative 4x squared plus 6x minus 6. We see that in blue. I graphed the line that I wanted to be parallel to, 6x plus y equals 8. That's the red line. And then I graphed my final answer, and look how beautiful that is. There is the point of tangency right there. Well, it's kind of hard to locate exactly. But right there around 1.5, there it is, 1.5, 3 halves, comma negative 6. And then again, the purple line is perfectly tangent to the function and parallel to the red line. How cool is that? So it's kind of like a working backwards problem. So being parallel means I have the same slope. Set the derivative equal to that slope and then solve for x. That's going to be your point of tangency. Don't forget to also find your y-coordinate using the original function. And then all you got to do is put it all together. It's really kind of simple. All right, let's try another one here. So we're going to find the equation of the line that's tangent to the function 2x minus 1 over 4x plus 3 and parallel to the line y equals negative 10x plus 25y equals 25. All right, so the first thing I need to know what my slope is, because if I'm parallel, I instantly know I have the same slope. So that's actually going to save us a lot of time. So we have 25y equals positive 10x plus 25. Again, all you got to do is solve for y to get into slope-intercept form. Divide everything by 25. I get y equals 10 over 25x plus 25 divided by 25 is 1. And that is reducible here. Let's see here. Both of 10 and 25 are both reducible by 5. So we get 2/5 x plus 1. So I now know my slope is 2/5. So the question is, what is the point of tangency, right? Because I know that there's millions of lines that have a slope of 2/5, but I want to be the very, very specific line that is also parallel to this given function, or excuse me, tangent to this given function. So I got my slope, which allows me to be parallel, but now I need the point of tangency. So once again, that's what the derivative is for, right? The derivative, you plug in x, you get the slope. But if I already know the slope, I can solve backwards to find the x, the point of tangency. So without further ado, the most important thing I need right now is the derivative. And there's my derivative with just a little bit of work of the quotient rule. Wasn't too bad, but the derivative is 10 over 4x plus 3 quantity squared. So now again, what I don't have, I have the slope, right? Boom, I have the slope, so awesome. What I don't have is my point of tangency. Don't have that point of tangency x comma y. But again, the x value that produces this slope from the derivative is that point of tangency. So what I have to do is take my derivative, 10 over 4x plus 3 squared, and set it equal to 2/5 and solve for x. Now this work's going to be a little bit detailed, so I'm going to give myself a little bit more space here. And again, this is where that algebra comes in that I told you guys all about. All right, let's see. So the first thing I'm going to do is cross multiply. I get 2 times 4x plus 3 squared equals 50. Then I actually have to do the squaring first, order of operations. That's going to be 16x squared plus 24x plus 9 equals 50. Distribute that 2. We get 32x squared plus 48x plus 2 times 9 is 18 equals 50. Then remember, this is a quadratic. To solve a quadratic, I got lots of options, but again, I got to get a 0 on one side, so I'm going to subtract that 50 over. 32x squared plus 48x, subtract that 50 over. 18 minus 50 is negative 32 equals 0. Now, I'm going to give you 3 different ways that you could solve this for x to get your x value that I'm looking for. 1, factor. 2, quadratic formula. 3, graph this in Desmos or on your calculator and find the zeros, because where this function crosses the x-axis is where it's equal to 0, so those would be your answers. But you know what? I'm going to go ahead and factor. And here's how I'm going to factor, because I love to factor. Now, most of you are going to probably want to use the quadratic formula because it looks kind of ugly, or maybe you're going to want to just go ahead and use Desmos. But again, I'm going to factor. All terms are divisible by 16, so I'm going to factor out at 16. I get 2x squared plus 3x minus 2 equals 0. And then I'm going to go ahead and factor. Let's see here. This isn't too bad. I get 2x times x is 2x squared. 1 times 2 is the 2 in the back. But let's see, I want that to be positive and this to be negative. That way I get a 4x on the outside, a negative x on the inside, which makes the 3x. So now that I factored this, I could use the zero product property to get that 2x minus 1 equals 0, which means x equals positive 1/2. Or x plus 2 equals 0, which means x equals negative 2. So yes, there are going to be 2 answers. I automatically know my slope is 2/5. I can't change that because if I want to be parallel to that given line, I got to have a slope of 2/5. But apparently there are 2 points of tangency on this function that will create the line I'm looking for. One of them has an x value of 1/2 and the other has an x value of 2. So of course now I need to go ahead and find my y coordinates, and then I'm actually show you a graph so you can understand how this is all correct. But I'm going to find my y coordinates by plugging back into the original function. So here is my original function. So I'm going to plug in 1/2 to get the y coordinate when x equals 1/2. So that's 2 times 1/2 minus 1, all divided by 4 times 1/2 plus 3. Let's see here, 2 times 1/2 is 1, 1 minus 1 is 0. 4 times 1/2 is 2, 2 plus 3 is 5, but it doesn't matter. I'm going to get 0. So that one point is at 1/2 comma 0. And then the other point was when x equals -2. And, I said positive. No, I said -2. I just forgot to write the negative right there. Okay, so again, plugging -2 in, that's 2 times -2 minus 1, all divided by 4 times -2 plus 3. That's on top, -4 minus 1 is -5. On the denominator, 4 times -2 is -8. -8 plus 3 is also -5, so I get +1. So that point there is -2 comma 1. So again, the 2 points of tangency are 1/2 comma 0 and -2 comma 1. Now I really want to show you a graph of this so you could truly understand how the heck there's going to be two solutions here. It's actually pretty cool, and this is the power of really using Desmos to take a look at this. So in Desmos here, I graph the original function, 2x minus 1 divided by 4x plus 3. That's the blue function we see there. That is a rational function as an asymptote. And then I graph the black line, which is the line that I want to be parallel to, but I also want to be tangent to the given function. And then I graph the 2 points that I fact with doing a little bit of good old algebra work. And that point was 1/2 comma 0, that's the red point, and -2 comma 1, that's the blue point. So you can actually see that there would be two lines that meet what I'm looking for. I'm looking for lines that are parallel to the black line and tangent to my function. So I see this, you can kind of envision, I'll draw it on the graph here in a second once we get it, but you can almost envision the line that's going to be tangent to this point and parallel to the black line, and then another one over here that's tangent to the red point and parallel to the black line. So now, of course, we got to go and actually find those, equations of those lines. So again, I'm going to create two equations. The one thing they share in common is they have the same slope. So y minus 0 equals 2/5 times x minus 1/2. That's going to be the first line I'm looking for. And the second one's going to be y minus 1 equals 2/5, same slope, times x plus 2. Again, when you subtract a -2, you get a +2. So now I can actually go back to Desmos and add those points in, or those graphs in. You'll see how they connect. So here's the first one, y minus 0 equals 2/5, that was my slope, times x minus 1/2. And boom, look how cool that is. You can literally see that green line perfectly be tangent to my blue function and parallel to my black line. And the second line was y minus 1 equals 2/5 times x plus 2. Sorry, I was a little slow there on my typing. And there it is. Again, look how beautiful this looks, right? There's my purple line that once again is clearly parallel to the black line, has the same slope, and tangent to that blue function. So what a cool set of problems, right? I think these problems are really awesome. They really give you some power with a derivative. But the key thing is, because you want to be parallel to a given line, it means you want to have the same slope. What you don't know is that point of tangency. But again, remember, this is the value of that x. X is so powerful because if you plug x into the function, you get y. If you plug x into the derivative, you get the slope. But if you already know the slope, you could solve backwards to get that x value. And that's how cool it is. And in this example, there's actually two answers. And again, I can't recommend using Desmos enough to really visualize what it is you're finding and confirm that you actually found what you were intending to look for. All right, get ready for Fun with Derivatives Part 3, when we will take a look at that really fantastic fourth type of problem that's really going to be a good old head scratcher. They're really good fun problems. All right, guys, see you in the next video.